Hello and welcome. In this video, we're going to take a look at antiderivatives of functions. Now, antiderivatives are just sort of the gateway into integral calculus. It bridges the gap between differential calculus, where we're taking the derivative of something, and integral calculus, where we are looking at the integral of a function. So, we know what a derivative is, but what is an antiderivative? Well, it's kind of easy to define an antiderivative in terms of the derivative. Let's say that capital F is the antiderivative of a function little f. Well, if it's the antiderivative of little f, then taking the derivative of capital F should be equal to f. That's the idea. Antiderivative is the opposite of the derivative. By taking the derivative of the antiderivative of a function, we should get the function itself. Now, the operation of finding an antiderivative, we don't just call that anti-differentiating. That's quite a mouthful. When we want to find the derivative of something, we use the differentiation operator. When we want to find the antiderivative of something, we use the integration operator. And it kind of looks like this elongated S. And we also need to specify what the independent variable is that we are finding the antiderivative with respect to. And so the integral symbol is placed in front of the function to be integrated, called the integrand. And then after the integrand, we have what's called a differential. dx means that we are taking the integral with respect to x. We are finding the antiderivative of f of x with respect to x. Now, if capital F is an antiderivative of a function f of x, then the general antiderivative is actually capital F of x plus an arbitrary constant c. Now, why is that? Let's stop and think for a second. Let's say we wanted to find the antiderivative of the function 2x. Well, based on the definition of what an antiderivative is, I should be looking for a function that has a derivative equal to 2x, and that would be the x squared function. And sure enough, that is an antiderivative of 2x. But the function x squared isn't the only antiderivative. In fact, I could have the function x squared plus 1, which also has the derivative 2x, or x squared plus 2, or maybe x squared minus 1. In fact, x squared plus any constant would still have the derivative equal to 2x. And maybe this wouldn't be a surprise because all of these functions have exactly the same shape, just being moved up or down. And seeing that all of these have the same shape, it seems that they would all also have the same derivative. All right, so with that in mind, we can then start just trying to reverse many of the rules that we learned for differentiating a function. So with that concept in mind, we can start trying to reverse all of the rules that we learned for finding the derivative of a function. Now, in that last example, we really just used what's called the power rule. We're used to the power rule for finding the derivative of a function, where we simply just drop the power in front and it becomes the new coefficient, and we reduce the power by 1. But now we have to reverse that process, and so we start by increasing the power by 1 and then dividing by the new power. However, what's going to be a little bit of a problem here is in the case where n is equal to minus 1. But that's okay, we'll deal with that in a moment. Don't forget, though, that when we apply the power rule, we should always add an arbitrary constant. Now, if we are just trying to find the antiderivative of a constant k, or when the power of x is 0, then when we find the antiderivative of a constant, our antiderivative should be that constant k times x plus some arbitrary constant. And we'll refer to this plus c as the constant of integration. Now, much like the constant multiple for derivatives, if we have a constant multiple of some function that we wish to find the antiderivative of, then we'll just hold on to that constant multiple and we can find the antiderivative of the function itself and then multiply by the constant. So this integral of c times f of x is simply the integral of f of x to find the antiderivative first and then multiply by c. Similarly, when we were differentiating several terms of a function, we could just differentiate one term at a time. Well, likewise with integrals, if we have multiple functions, perhaps powers of x, being added or subtracted, then we'll simply find the integral of each individual term. And that's just going to be finding several antiderivatives. Now, a little note about this is every time we integrate a function, we would end up with a plus c. However, if we end up with multiple arbitrary constants, maybe we would call the first arbitrary constant of integration c1, and maybe we would call the second constant of integration c2. Well, c1 plus c2 add together and still would be a constant. So typically, when we are splitting up an integral into multiple integrals, we simply include a single arbitrary constant plus c at the end of all of our integration process. Now, how about another couple easier derivative rules that we can reverse? We saw that the derivative of the exponential function, e to the x, was very simple. The derivative of e to the x was e to the x. And so, not only is e to the x its own derivative, but e to the x is also its own antiderivative. And so our natural exponential rule says that the integral of e to the x dx is e to the x plus c, because the derivative of e to the x plus any constant would still be e to the x. And we also saw that when we took the derivative of the natural logarithmic function ln x, that we just got 1 over x. And remember that the domain of ln x needs to have x greater than 0. But let's say we wanted to reverse that. If we wish to find the antiderivative of the function 1 over x, then sure, that would be the natural logarithm of x plus c. But that would only be if x is greater than 0. But 1 over x is actually a function that's defined for negative values of x too. So if we wanted a little bit more of a general form, the antiderivative of 1 over x dx is equal to the logarithm of the absolute value of x plus c, so long as x is not equal to 0. And there we go. That gives us a lot of the building blocks that we just learned from differential calculus, but reversed in order to get an established form of integrals for integral calculus. We're still going to be learning many other techniques, and of course, like many inverse operations, the integration operation can be a lot more difficult than the differentiation operation. Well, let's try several examples of functions using these types of rules and take a look at antiderivatives. Now, this integral that we're using, the integral symbol of f of x dx, we call this the indefinite integral. And it's kind of a key term there because when we're looking at some of the applications of integration in another video or two from now, we will also have what's called the definite integral. The indefinite integral, what we're talking about right now, is the process by which we find the most general form of the antiderivative. So indefinite integrals will have this plus c at the end. Now, if c is an inconvenient letter, because you may be dealing with something like a cost function or marginal cost function, something that already involves a c, then really any letter will do. We just need to make sure that we add some arbitrary constant to give the most general form of the antiderivative. Starting off with a power rule example. If we wish to find the indefinite integral of x to the 5 with respect to x, that means that we're looking for an antiderivative of x to the 5 with respect to x. So applying the power rule, we're going to raise the power by 1, and that gives us x to the 6. And then we're going to divide by that new power, which is 6. And don't forget to add our plus c. Now you can check your answer with differentiation. And sure enough, the derivative of x to the 6 over 6 plus c is equal to 6x to the 5 over 6, which is equal to x to the 5. Adding in some constant multiple rules and sum and difference rules, then we can start taking a look at polynomials. The antiderivative of 3x squared, well, being a constant multiple, we could leave this 3 behind and then take the indefinite integral of x squared. Looking at the next term, we can leave the 2 behind and look at the indefinite integral of x. And then we have the indefinite integral of 4. So this can really be split up into 3 separate integrals. And when we are looking for the antiderivative of each of these 3 functions, again, we could add a c1, a c2, and a c3 being the 3 different constant of integrations, but when they combine together, they would just form a single constant anyways. So a form for the most general antiderivative would be 3 times x cubed over 3 plus 2 times x squared over 2 plus 4x, and then we add our constant of integration plus c. And this can be simplified to equal x cubed plus x squared plus 4x plus c. And that's a fairly easy one to check. The derivative of x cubed is 3x squared, the derivative of x squared is 2x, the derivative of 4x is 4, and the derivative of a constant is 0. Okay, to make things a little bit more challenging now, let's start adding in some functions where we have a constant over x and maybe a few powers that aren't exactly whole numbers, and let's throw in the exponential function. So an antiderivative of 6 over x plus 2e to the x plus the square root of x. Well, again, we could split this up into 3 separate different functions and integrate each single one. 6 over x is a multiple of 6 times the function 1 over x. 2e to the x is a multiple of 2 times the natural exponential function e to the x. And root x can be written out as a power. And now, because we don't really know whether or not x is greater than 0 or less than 0, we simply know that x cannot equal 0 for the integrand to be defined in the first place. We should use the natural logarithm of the absolute value of x. And the antiderivative of e to the x is going to be one of our favorites here. And then be careful when we have a fraction, x to the 1/2, we're going to have to add 1 to the power, and then we're going to have it divide by the new power. But if we're dividing by a fraction, divided by 3/2, it's much easier just to multiply by the reciprocal. So we'll multiply by 2/3 instead of dividing by 3/2. And then don't forget, for the most general form of the antiderivative, we need our constant of integration. All right, well, let's try an application of this with respect to economics. Let's suppose that the marginal cost of each pair of shoes decreases by 50 cents a unit for each additional unit produced due to some savings in the materials to produce the pair of shoes. And let's say that the marginal cost of the 101st pair of shoes is $60. All right, well, let's give the marginal cost function, and then let's take a look at looking for the monthly total cost function if we are given fixed costs of $3,000. Well, first of all, we know that marginal cost is decreasing by 50 cents per unit for each additional unit. And that is actually the rate at which marginal cost is changing. And when we think about the rate of change of marginal cost, that's the derivative of marginal cost. So really we know from our given information that c double prime of x is negative 0.5, since costs are decreasing by approximately 50 cents for each new pair of shoes. If we want to find the marginal cost function c prime, but we have the derivative of marginal cost, we need to look for an antiderivative. So to get marginal cost c prime, what we're going to do is we're going to integrate the rate at which marginal cost is changing, which is negative 0.5, with respect to x. Now this is just a constant, so applying the constant function rule, we end up with c prime of x equal to negative 0.5x plus an arbitrary constant, and I really shouldn't use c here, so why don't we use something like k? Now the importance of that arbitrary constant k here is the fact that we do actually have some information about what marginal cost ought to be when x is equal to 100. We know that c prime of 100 is equal to $60. Since the marginal cost of the 101st pair is $60, that is saying that the increase in cost from 100 to 101 is 60. So we set c prime of 100 equal to 60, we plug in x is equal to 100, and we set that equal to 60. So what does k have to equal? Well, k would have to equal 110. So putting these two pieces of information, the most general antiderivative, plus some sort of condition that's given to us, the antiderivative that we are looking for, the marginal cost function, must be negative 0.5x plus 110. And now that we've got the marginal cost function, we can take a look at part B. Knowing about the fixed cost per month, we want to give the total monthly cost function c of x. Well, remember that marginal cost is telling us how quickly total cost is increasing per unit. So again, this is a rate of change. This is the derivative of our monthly total cost function. So by integrating marginal cost, we would get total cost. So to find our cost function, we'll start off with the most general antiderivative of our marginal cost function. And this is just going to be a constant function, a power rule, and a constant multiple rule. So keeping our negative 0.5, that is going to get multiplied by the antiderivative of x, which is x squared over 2. And that gives us negative 0.25x squared. And then we have our plus 110, which is a constant, so its antiderivative is 110x. And then we add our arbitrary constant at the end. Now I could again use k, but I've already used k. I shouldn't use c. Well, why don't we use f here? Why am I using f? Well, right away you see that when x is equal to 0, I'm just left with this constant. And that is precisely what fixed costs are. We're given some information that the cost to produce 0 units in a month is still going to be a fixed number, 3,000. So really we know that f is equal to 3,000, and that is our fixed cost. So once again, we take the most general antiderivative plus some information about the problem, and we can form the antiderivative that is applicable to our problem. The monthly cost function is negative 0.25x squared plus 110x plus 3,000. And now we can just go ahead and plug in any level of production for a given month and find the total cost. Well, I hope that kind of at least opens the door to integral calculus. We know how to talk about an indefinite integral at this point in time. An indefinite integral is nothing more than reversing differentiation. So if we're given some sort of rate of change of a quantity by finding the antiderivative of it, then we have an expression for the given value of that quantity at some moment. The arbitrary constant, our plus c, that is a very relevant piece of information depending on the application. If we're given additional information about a point on the antiderivative curve, then we know exactly which of that family of curves is the correct one for our model. So, you usually have some sort of initial value or some sort of known point that you can plug in to be able to find out what the arbitrary constant is. Now we'll take a look at how this is going to solve some other very important problems in calculus in the future, but we'll save that for later. Thanks for watching, and I'll see you in the next video.